Okay, this video is to remind us of algebra tiles and how to combine like terms when we're in algebra. So let's take a look. And on this page there are three tiles. The long green rectangular tile is the one that we call the X. Okay, this is our X tile, and we'll talk about why in a minute. The blue one is called our X squared tile. And basically you can remember it's a square because the shape of the blue tile is a square. And the symbol for square is the exponent 2. And our little tiny yellow square guy is called our one piece. It's our base unit, any one unit, okay? So let's take a look at why we have them named the way that we have them. Alright, so this little yellow square we called a 1 unit, and that meant that his area was a 1. And I have to remind you that area is length times width. That means the length of this shape from here to here and the width of the shape from here to here have to multiply together to make a 1. Well, what times what makes 1? The only answer could be is 1 times 1. So what that means is the length of this guy is a 1, and his width is also a 1, and 1 times 1 makes 1. That his area is 1. We also call these units or constants. So in math, any number that doesn't have a variable attached to it, like 1, 2, 3, 4, 5, 10, 100, 20, 25, these are all constants. They're units. And so over here, I have 5 yellow squares. These are 5 units, or they're representing the number 5, okay? So what I want to do is I want to show you how this makes our x square what it is. If we know our little yellow guy is a 1, we can take him and we can add him to, we can move this little constant or 1 unit over to our green guy, and we can see that the length of this green one is a 1. His length is the exact same length as the yellow, so that makes his length 1. Well, let's figure out if we can, what his width is. So if we take our yellow units and we try to line them up and stack them next to the width of this green shape, we can see that even if we're trying to be as perfect as possible, there is no exact measurement for the length of this green shape. That means his measurement is unknown. So that means something that we call unknown, we label as an x. So now to find the area of this green shape, we would have the length of 1 times the width of x, and 1 times x makes x. So that makes the area of this shape an x, which is why we call him the X piece, okay? Now coming over to this blue, this multicolored shape over here, you can see that the length of our blue shape from here to here is the same as the length of our green guy, and that length was X. So this side is an X value. And the same thing here. This side over here, his length is the same as our green guy, which makes it an X. And X times X makes X squared. Okay, and that's where we get the name X squared for our blue pieces. Okay, so if I'm given a problem like 4x plus 3 plus 2x plus x squared plus 4, I need to combine my like terms. Well, by looking at these algebra tiles, you can see that they're very different. So x's are green, x squares are blue, and they're different shapes, which means that they cannot be combined. I cannot say how many green pieces do I have and combine blues and greens. So x's are the green ones, x squares are the blue ones. So therefore when I read my problem 4x, I have to think, okay, I really have 4 of these x shapes. Okay, and I'm adding it to 3. Well, numbers are units, and they are these 3 little yellow guys. And I'm adding that to 2 more x's. And I'm adding that to an x square. How many x squares? Just 1. because there's an invisible 1 sitting in front of that x squared. And then I'm adding it to 4 little pieces. So there we go. Now that's my math problem using algebra tiles. But what I have to do is I have to combine my my shapes and figure out what my problem is. So I scooted all my extra algebra tiles over to the corner so that I can rearrange what I'm working with and combine my like terms. So combining like terms says move all the green guys next to each other. How many do I have? Well, that makes 6 x's because 6 green shapes, and green shapes are x's. Okay? And then if I combine all my little yellow guys and move them all next to each other, I really have 1, 2, 3, 4, 5, 6, 7 of the yellow guys. And the yellow guys are called our unit pieces or our numbers. So that's really that I'm adding 7 to them. And then I have 1 blue guy, and the blue guys are called our squares. So I have 1x squared. So this is my problem. However, in algebra, we always go from biggest piece to smallest piece. And since my x squared is my biggest piece, I would write him first. Then I would write my x's. Then I would write my 1 units. Okay? Or my constants is the name that our 1 units are called, constants. So my final answer becomes x squared plus 6x plus 7. So if I'm doing this problem, 3x squared plus 2x plus x squared plus 7 plus 5x, again, I'm just combining like terms. If I have algebra tiles, I can move them and put them out, or I can start to see that x squares are the square pieces. And so in order to combine x squares, I have to combine this guy with other like-minded pieces. And that means that everything has to be x squares. So I have another one right here. And so to combine them, I'm saying I'm adding 3x squared plus x squared. So let's write it in that order. I'm going to add these guys together. And by moving these guys around and putting them next to each other, I'm using the commutative property of addition, which means I can add anything in any order that I want. The next thing that I really want to combine is my single x's. So I have a 2x and I have a 5x. So I'm going to write them, and I'm going to put them next to each other so that I can add them together. And then I'm left with just this constant, a positive 7, and I'm going to put him at the end. Now I'm going to combine my pieces, my like-minded pieces. So I can get out my little algebra tiles and I can say I have 3x squares. 1, 2, 3, and I'm adding it to 1 more x squared. Well, how many do I have? I have 4. So I have 4x squares. I'm done with that piece. And I'm going to add it to the next component, which is 2x plus 5x. And again, if I want, I can get out my algebra tiles, or I can draw and say I have 2 x's, and I'm adding it to 1, 2, 3, 4, 5 x's. How many x's do I have altogether? I have 7 x's. So I'm going to put that I have 7x. And I'm adding it to my constants. I'm done with that piece. So I have 7, but I have nothing else to add it to. So I'm just going to put my 7 here. And this becomes my final answer. So I have 2 problems here. 3x plus 2 plus 4x plus x. And another one, 4x plus 3 plus 7x plus 5. And what I'd like you to do is I'd like you to pause the video and try to solve these problems. You can use your algebra tiles, you can draw it out, or you can just use algebraic math. After you're finished, then check back. So problem number 1 is 3x plus 2 plus 4x plus x. And I always write my original problem, always, every single time. And now I'm going to use the commutative property of addition, and I'm going to move the like-minded pieces next to each other. So I'm going to say that if I move them around and I put all of my x's next to each other, that it is still equal to that first line, which is why I put the equal sign. And now I'm going to add my like-minded pieces. 3x plus 4x is 7x, plus x is 8x. and I'm still left with my constant of a 2. So that is the answer to problem number 1. Problem number 2 is 4x plus 3 plus 7x plus 5. And again, I always write my original problem. Then next step is I'm going to say, all right, I'm going to set it equal to things, but I'm going to just manipulate the problem and move like-minded pieces next to each other. So 4x and 7x are the same, so they're going to go next to each other. And the 3 and the 5 are both constants, and they're going to go next to each other. And now I'm going to solve. 4x plus 7x is 11x's, and 3 plus 5 is 8. And this becomes my final answer for problem number 2. Okay, this sample problem is a little bit harder. It has those negatives in there, and it works the same way. So the first thing that we do is we want to put all of the like-minded things next to each other. So I have an x squared piece here, and I have a negative 2x squared piece over here. So I'm going to put them next to each other. And it reads x squared minus 2x squared. Okay, I wrote them. Now I'm going to deal with my next piece, my x's. I have a positive 3x and a positive 3x. So I'm going to write them next to each other. And notice how when I circle them, I know that I'm finished with them. Now I'm going to have my negative 2 and my negative 7. And I'm going to write them. And now everything is in, it's all exactly the same, which is why it's equal to, but they're next to the people that they need to be combined with. Now the next rule of algebra, the basic is that we never subtract in algebra. We always add the opposite. So I'm going to change all my subtraction signs to addition and change the power. And now I'm going to start combining my like terms. So I have x squared plus a negative 2x squared. So that means I have this squared piece and I have two negatives. So usually I show my negatives as the colored in pieces. If you're using real algebra tiles, they're usually red because red means subtract or negative. So if I have one positive x squared and two negative x squares, well, we know that a positive and a negative cancel out and they make a zero pair, which means that I'm left with only one negative x squared. So I can write that. I have a negative x squared left when I combine those two pieces. And now I'm going to look at my positive 3x plus a positive 3x. So if I need to draw it, I can. 1, 2, 3. And they're positive, so they're white. And now I have 3 more, 1, 2, 3, and they're all positive, so they stay white. So I have a positive 6x. And now my last component is my constants. I have a negative 2 and a negative 7, and they're being added together. So again, I can draw them out and say that I have negative 2, which would be the colored in ones, and then I have negative 7. And here's 7, but to make them negative, I would color them all in. And how many negatives do I have? I have 9 negatives. So I would write I have 9 negatives, or I can write adding a negative 9. Either way. And this becomes my final answer. Okay, so these 4 problems are a little bit harder. I want you to practice them, try them at home tonight, and bring your 4 problems back with you to class tomorrow. So make sure that you can draw them or use your algebra tiles, and make sure you show your algebra steps logically down your paper the way that I've been modeling them for you. And remember, you're combining like terms.